In 1961, astronomer Frank Drake sat down with a simple equation that would fundamentally change how we think about our place in the universe. The Drake equation attempted to estimate the number of communicating civilizations in our galaxy. When Drake plugged in his optimistic numbers, the result was staggering. Thousands, perhaps millions of alien civilizations should exist in the Milky Way alone. Yet here we are, over 60 years later, and we have found absolutely no evidence of extraterrestrial intelligence. This is the central paradox of our cosmic existence. The universe appears perfectly suited for life. The numbers suggest we should have company, but the silence is deafening. Today, we'll explore this profound mystery in depth. We'll examine the mathematical arguments for alien life, investigate the various explanations for why we haven't found them, and consider what recent scientific discoveries tell us about our cosmic solitude. This is not just a question about aliens. It's a question about the nature of intelligence, life, and our own future as a species. The stakes couldn't be higher. The answer to whether we're alone will fundamentally reshape our understanding of biology, consciousness, and humanity's role in the cosmos. So let's begin this journey into one of science's greatest mysteries: the mathematical case for alien life. To understand the alien paradox, we must first grasp the sheer scale of the universe. Our home galaxy, the Milky Way, contains approximately 400 billion stars. That's 400 billion individual suns, each potentially warming its own family of planets. But the Milky Way is just one galaxy among an estimated 2 trillion galaxies in the observable universe. Let's put this in perspective. If you counted one star per second, it would take you over 12,000 years to count all the stars in our galaxy alone. To count every star in the observable universe would require more time than has passed since the Big Bang, about 13.8 billion years. Now, thanks to missions like Kepler and TESS, we know that planets are incredibly common. Current estimates suggest that nearly every star hosts at least one planet. More importantly, we've discovered that Earth-sized planets in the habitable zone, that perfect distance where liquid water can exist, are found around roughly 20% of Sun-like stars. This gives us approximately 40 billion potentially habitable planets in our galaxy alone. 40 billion worlds where the temperature is just right for liquid water, where the building blocks of life as we know it could potentially take hold and flourish. But let's be even more conservative. Let's say only 1 in 1,000 of these planets actually develops life. That still leaves us with 40 million life-bearing worlds in the Milky Way. And if only 1 in 1,000 of those develops intelligent life capable of technology, we're still looking at 40,000 technological civilizations in our galaxy. The Drake equation formalizes this thinking. It considers factors like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction that actually develop life, the fraction that develop intelligent life, the fraction that develop detectable technology, and how long such civilizations last. Even with pessimistic estimates for most variables, the equation suggests we should not be alone. Carl Sagan once calculated that there could be 1 million communicating civilizations in our galaxy. More recent estimates range from dozens to millions, but almost no serious scientist calculates that the number should be 0. This mathematical argument becomes even stronger when we consider time. Our sun is relatively young compared to many stars in the galaxy. Billions of stars formed billions of years before our solar system even existed. If life evolved on planets around those older stars, some civilizations could have had a head start of several billion years. 1 billion years is an almost incomprehensible amount of time for technological development. Consider that human civilization has existed for only about 12,000 years, and we've had radio technology for barely 100 years. What could a civilization accomplish with a billion-year head start? Such ancient civilizations might have already colonized the entire galaxy multiple times over. They might have built megastructures around stars to harness their energy, created self-replicating machines to explore every star system, or developed into forms of existence we can't even imagine. Yet we see no evidence of any of this. No radio signals, no megastructures, no obvious signs of galactic engineering projects. The universe appears as pristine and natural, as if intelligence had never arisen anywhere except on Earth. the Fermi paradox emerges. The contradiction between the mathematical expectation of alien life and the complete absence of evidence was crystallized by physicist Enrico Fermi during a lunch conversation at Los Alamos in 1950. While discussing flying saucers with colleagues, Fermi suddenly asked, "Where is everybody?" This simple question encapsulates what we now call the Fermi paradox. If the universe should be teeming with life, if civilizations should be common, if some should be billions of years ahead of us technologically, then where are they? Why haven't they contacted us, colonized Earth, or at least left some detectable trace of their existence? The paradox has only grown stronger with time. When Fermi posed his question, we didn't know if other stars had planets. We didn't know how common the building blocks of life were in space. We didn't know how quickly life could emerge under the right conditions. Today, we know that all of these factors favor the existence of life. Exoplanets are everywhere. Organic molecules float freely in interstellar space. We've found life on Earth in every conceivable environment, from the crushing depths of ocean trenches to the radioactive interior of nuclear reactors, from the near vacuum of the upper atmosphere to the superheated water around volcanic vents. Life appears to be remarkably adaptable and resilient. It emerged on Earth almost as soon as conditions allowed, suggesting that the transition from chemistry to biology might be relatively easy given the right circumstances. Moreover, we've begun to understand that intelligence itself confers enormous survival advantages. Intelligent species can adapt to changing environments, manipulate their surroundings, and eventually escape the gravitational bonds of their home planet. Intelligence seems like an evolutionary inevitability given enough time and diversity. Yet the silence persists. We've been listening to the cosmos with increasingly sophisticated instruments for over half a century. We've analyzed the light from thousands of distant stars looking for signs of artificial megastructures. We've studied the atmospheres of nearby exoplanets, searching for the chemical signatures of life. We've sent messages toward nearby star systems and listened for replies. The result has been a cosmic silence so profound that it has forced scientists to question our most basic assumptions about life, intelligence, and our place in the universe. Some researchers have calculated that if galactic colonization were possible, it should take only a few million years for a single civilization to spread throughout the entire Milky Way, a blink of an eye in cosmic terms. The fact that this apparently hasn't happened suggests either that we're completely wrong about the prevalence of life, or that there are forces at work that we don't yet understand. The rare Earth hypothesis. One possible resolution to the Fermi paradox is both simple and sobering. Perhaps we really are alone, or at least exceedingly rare. This idea, formalized as the rare Earth hypothesis by paleontologist Peter Ward and astrobiologist Donald Brownlee, suggests that while simple life might be common in the universe, complex life, and especially intelligent life, requires such an extraordinary confluence of factors that Earth might be unique, or nearly so. Consider the remarkable chain of events that led to our existence. Earth orbits at precisely the right distance from the Sun to maintain liquid water for billions of years. Our star is unusually stable and long-lived. We have a large moon that stabilizes our planet's axial tilt, preventing wild climate swings that could make complex life impossible. Jupiter acts as a gravitational vacuum cleaner, deflecting many asteroids and comets that might otherwise bombard Earth. Our planet has active plate tectonics that regulate temperature and recycle nutrients. We have a magnetic field that protects us from deadly cosmic radiation. The list goes on and on. But perhaps even more important are the biological hurdles that life on Earth has somehow overcome. The transition from simple prokaryotic cells to complex eukaryotic cells, cells with nuclei and sophisticated internal structures, appears to have happened only once in Earth's history, and it took over 1 billion years. This transition required one bacterium to successfully engulf another without digesting it, leading to a permanent symbiotic relationship. The engulfed bacteria became mitochondria, the powerhouses of complex cells. This seems like an extraordinarily unlikely event, yet without it, complex life as we know it couldn't exist. Similarly, the development of multicellular organisms, sexual reproduction, and eventually intelligence each represent major evolutionary leaps that might be far less probable than we assume. On Earth, It took over 3 billion years for complex life to emerge, and intelligence appeared only in the last few million years. The rare earth advocates point out that Earth has experienced several mass extinction events that came close to wiping out all complex life. The Permian extinction 252 million years ago killed 96% of marine species and 70% of terrestrial species. If such events are common on other worlds, the window for developing intelligence might be vanishingly small. Even more troubling is the realization that Earth's habitability is temporary. As our sun ages, it will gradually increase in brightness. In about 1 billion years, the increased solar radiation will create a runaway greenhouse effect that will boil away Earth's oceans. The window for intelligence on any given planet might be much narrower than we think. Recent discoveries have added both support and challenges to the rare Earth idea. We've found that many exoplanets are tidally locked to their stars, with one side permanently facing the star and the other in eternal darkness. We've discovered that many planetary systems are far more chaotic than ours, with giant planets migrating inward and disrupting the orbits of smaller worlds. On the other hand, we've also found life thriving in environments on Earth that we once thought were impossible. Deep beneath the ocean floor, in highly acidic hot springs, in the dry valleys of Antarctica, wherever we look for life on Earth, we seem to find it. This suggests that life might be more adaptable than the rare Earth hypothesis assumes. The debate continues, but the core insight remains troubling. Perhaps the universe is not as hospitable to intelligence as we once believed. Perhaps the emergence of technological civilization requires such a precise sequence of unlikely events that we might indeed be alone, or at least so rare that we'll never encounter another civilization. If the rare Earth hypothesis is correct, it places an enormous responsibility on humanity. We would be the universe's only known conscious observers, the only known instance of matter organizing itself to contemplate its own existence. Our extinction would represent not just the end of human civilization, but potentially the end of consciousness in our region of the universe. The Great Filter Theory. Perhaps the most unsettling explanation for the Fermi paradox is the concept of the Great Filter. Proposed by economist Robin Hanson, this theory suggests that there is at least one evolutionary step in the path from simple matter to expanding interstellar civilization that is extremely improbable. The Great Filter could be behind us or ahead of us, and the implications of each possibility are profound. If the filter is behind us, if the incredibly difficult step has already been overcome, then we are extraordinarily rare and precious. But if the filter lies ahead of us, then we face an existential threat that has destroyed every other civilization that has ever tried to pass through it. Looking at the history of life on Earth, we can identify several potential great filters in our past. The origin of life itself remains mysterious. Despite decades of research, we still don't fully understand how non-living chemistry transitioned to living biology. This step might be far more difficult than we assume. The development of complex cells was another major hurdle. For over 2 billion years, Earth was inhabited only by simple prokaryotic organisms. The evolution of eukaryotic cells, cells with nuclei and complex internal structures, represents a fundamental leap in complexity that might be incredibly rare. The emergence of multicellular life, sexual reproduction, intelligence, and technology each represent additional potential filters. Any one of these steps might be so improbable that most potentially life-bearing planets never achieve it. But what if the Great Filter lies ahead of us? This possibility is far more terrifying because it suggests that something systematically destroys civilizations before they can become truly spacefaring. Looking at our own species, we can identify several candidate filters that we have yet to successfully navigate. Nuclear weapons represent an obvious threat. We've possessed the ability to destroy our civilization for over 75 years, and we've come frighteningly close to nuclear war multiple times. The Cuban Missile Crisis, the false alarm during Able Archer 83, the malfunction of early warning systems. Any of these could have triggered a nuclear exchange that might have ended technological civilization. Climate change presents another potential filter. Our industrial civilization is rapidly altering Earth's atmosphere and climate in ways that could make the planet uninhabitable for complex life. Perhaps every technological civilization faces this same challenge. The energy sources that enable technology eventually destroy the planet's habitability. Artificial intelligence might represent an even more formidable filter. As we develop increasingly sophisticated AI systems, we face the possibility of creating artificial minds that surpass human intelligence and pursue goals incompatible with human survival. Many AI researchers believe there's a significant risk that advanced AI could lead to human extinction within the next century. Biotechnology offers another route to civilization-ending catastrophe. As our ability to engineer biological systems advances, it becomes increasingly easy for small groups or even individuals to create devastating biological weapons. Engineered pandemics could potentially wipe out most of humanity before we even understand what's happening. Other potential filters might be even more subtle. Perhaps civilizations become so absorbed in virtual realities that they lose interest in exploring the physical universe. Perhaps advanced societies invariably turn inward, focusing on internal experiences rather than external expansion. Or perhaps the filter is more fundamental. Maybe any civilization advanced enough to contemplate interstellar travel inevitably develops technologies that threaten their own existence, and very few manage to navigate this dangerous transition successfully. The timing of potential filters is crucial. If civilizations typically destroy themselves within a few centuries of developing radio technology, this would explain why we haven't detected any alien signals. We might be living through the most dangerous period in our species' history, with our survival far from guaranteed. Some researchers have suggested that we might be able to identify which filters are most likely by studying our own planet's history. If life emerged very quickly on Earth but took a very long time to develop intelligence, this might suggest that the origin of life is easy but the evolution of intelligence is hard. Conversely, if intelligence emerged relatively quickly once multicellular life was established, this might suggest that the great filter lies ahead of us rather than behind us, a deeply unsettling possibility. The great filter theory forces us to confront uncomfortable questions about our own future. Are we approaching the same existential challenges that may have destroyed countless other civilizations? Can we successfully navigate the dangers that our own technology has created? Our answer to the Fermi paradox might ultimately depend on our ability to answer these questions about ourselves. The dark forest hypothesis. One of the most chilling proposed solutions to the Fermi paradox comes from Chinese science fiction writer Liu Cixin in his novel, The Dark Forest. This hypothesis suggests that the universe operates under a cosmic sociology where revealing your location is tantamount to suicide. The logic of the dark forest theory is based on several assumptions about how civilizations might behave on a galactic scale. First, all civilizations have survival as their primary goal. Second, civilizations cannot know the true intentions of other civilizations. Third, technological advancement means that any civilization could potentially become a threat to any other civilization, given enough time. In this scenario, the universe becomes like a dark forest where every civilization is an armed hunter, moving quietly through the trees. The hunters know that other hunters exist, but they dare not reveal their location because doing so would invite immediate destruction from competitors who see them as a potential future threat. The dark forest hypothesis suggests that any civilization that broadcasts its location, as we have been doing with radio and television signals for the past century, is quickly eliminated by more advanced civilizations that want to prevent potential future competition. This would explain why we hear no radio chatter from alien civilizations. Any civilization that makes noise doesn't survive long enough to develop advanced technology. This theory gains some credibility when we consider how human civilizations have historically behaved when technologically advanced societies encounter less advanced ones. The track record is not encouraging. European colonization of the Americas, Africa, and Australia led to the destruction or subjugation of indigenous civilizations that possessed valuable resources or occupied desirable territories. On a cosmic scale, every habitable planet is potentially valuable real estate. Every civilization represents a potential future threat that might develop weapons of unimaginable destructive power. From this perspective, the safest strategy might indeed be to remain hidden and to eliminate any civilization that reveals itself. The hypothesis becomes even more disturbing when we consider the concept of chain of suspicion. Even if a civilization has peaceful intentions, they cannot be certain that other civilizations won't perceive them as a threat. And even if two civilizations trust each other, they cannot be certain that third parties won't see their alliance as a threat to be eliminated. This creates a paranoid equilibrium where the safest strategy is always to strike first and ask questions later. Any civilization that deviates from this strategy, any civilization that chooses openness over secrecy, gets eliminated from the gene pool of galactic civilizations. The dark forest theory might also explain why we haven't been contacted by benevolent alien civilizations. Even if such civilizations exist and have detected our signals, they might dare not respond for fear of revealing their own location to hostile civilizations that might also be listening. Some researchers have pointed out that our own solar system might be under observation by hidden alien civilizations who are waiting to see how we develop. If we prove to be aggressive and expansionist, we might be eliminated before we become a threat. If we prove to be peaceful and inward-looking, we might be allowed to continue existing. This hypothesis has profound implications for SETI and our attempts to contact alien civilizations. If the dark forest theory is correct, our radio signals might have already sealed our doom. Advanced civilizations might already be preparing to eliminate us before we become a threat to galactic stability. However, the dark forest hypothesis faces several criticisms. It assumes that all civilizations develop along similar aggressive lines, and that advanced civilizations remain paranoid and trigger-happy despite their technological sophistication. It's possible that truly advanced civilizations move beyond such primitive survival instincts. The theory also assumes that stealth is possible on a galactic scale, which may not be true. Highly advanced civilizations might be impossible to hide completely, especially if they're doing anything interesting with large amounts of energy. Nevertheless, the dark forest hypothesis serves as a sobering reminder that first contact with an alien civilization might not be the peaceful, enlightening experience that many people imagine. If other civilizations operate under different ethical frameworks or perceive us as a threat, our first encounter might also be our last. Technological transcendence theories. Another category of solutions to the Fermi paradox suggests that advanced civilizations don't spread throughout the galaxy because they have transcended the need to do so. These theories propose that sufficiently advanced civilizations turn their attention inward rather than outward, focusing on virtual realities, consciousness uploading, or other forms of technological transcendence that make physical space exploration irrelevant. Consider the trajectory of human technology over the past few decades. We've become increasingly absorbed in digital worlds, social media, video games, virtual reality, and online experiences that can be more compelling than physical reality. If this trend continues, future humans might spend most of their time in sophisticated virtual environments that offer experiences impossible in the physical world. An advanced civilization might create virtual universes with their own physics, populated with digital beings living digital lives. These virtual worlds could be far more interesting and diverse than anything possible in base reality. Why explore the empty vacuum of space when you can create entire universes limited only by your imagination? This concept becomes even more compelling when we consider the possibility of consciousness uploading. If an advanced civilization develops the ability to transfer consciousness from biological brains to digital substrates, they could achieve practical immortality. Digital beings wouldn't need planets, food, or even energy in the traditional sense. They could exist as pure information, experiencing eons of subjective time while using minimal physical resources. From this perspective, spreading throughout the galaxy might seem primitive and wasteful. Why build vast space habitats when you can create infinite digital worlds? Why mine asteroids when you can simulate any material reality you desire? An uploaded civilization might view physical expansion as the technological equivalent of living in caves. The transcendence hypothesis might also explain why we don't see obvious megastructures like Dyson spheres around distant stars. A civilization focused on computation rather than manufacturing might need only a tiny fraction of a star's energy output. Instead of building massive solar collectors, they might construct small, highly efficient computers that run complex virtual realities. Some versions of this theory suggest that we might already be living in such a simulation, created by a post-human civilization as a form of entertainment or historical research. This idea, while unprovable, has gained serious consideration from philosophers and physicists who point out that if consciousness uploading becomes possible, simulated beings would vastly outnumber biological ones. Another form of technological transcendence might involve engineering consciousness itself. Advanced civilizations might develop the ability to modify their own minds, enhancing intelligence, eliminating negative emotions, or achieving states of consciousness that we can't even imagine. Such beings might find physical reality mundane compared to their enhanced subjective experiences. The transcendence theory also encompasses possibilities that are harder to envision. Advanced civilizations might discover entirely new physics that allows them to exist in higher dimensions or alternate realities. They might learn to manipulate time, space, or consciousness in ways that make our current scientific understanding seem childishly simple. These theories offer a somewhat comforting explanation for the Fermi paradox. Alien civilizations exist, but they've moved beyond the need for obvious physical expansion. They're all around us, but they exist in realities we can't perceive or in forms we don't recognize. However, transcendence theories face their own challenges. They assume that all advanced civilizations would make the same choice to turn inward. It seems likely that even in a transcended civilization, some individuals would retain curiosity about physical reality and want to explore the galaxy. Moreover, these theories don't easily explain why we see no evidence of even early-stage civilizations that haven't yet transcended. If technological civilizations are common, we should see at least some that are still in their expansionist phase, building obvious megastructures and sending out radio signals. The transcendence hypothesis might be more applicable to very advanced civilizations that have had millions or billions of years to develop. But even then, it's hard to imagine that every single advanced civilization would make identical choices about how to use their technology. The search for extraterrestrial intelligence. Despite the theoretical challenges posed by the Fermi paradox, the search for extraterrestrial intelligence continues with unprecedented sophistication and scope. The SETI Institute, founded in 1984, represents humanity's most systematic attempt to detect signals from alien civilizations. Traditional SETI searches focus on radio signals, based on the assumption that radio represents an efficient way to communicate across interstellar distances. The famous WOW signal, detected by Ohio State University's Big Ear Radio Telescope in 1977, remains the most intriguing candidate for an artificial signal, though it was never detected again despite extensive follow-up searches. Modern SETI has expanded far beyond radio searches. Optical SETI looks for laser pulses that might serve as interstellar communication beacons. These searches have the advantage that laser signals can be extremely bright and would stand out clearly against the cosmic background. The Breakthrough Listen project, funded by Russian billionaire Yuri Milner, represents the most comprehensive SETI search ever undertaken. Using some of the world's largest radio telescopes, Breakthrough Listen is surveying 1 million nearby stars, the entire galactic plane, and even nearby galaxies for signs of artificial signals. But SETI has evolved beyond just listening for deliberate messages. Researchers now search for technosignatures, any observable consequences of alien technology. This includes looking for artificial lights on the night side of distant planets, atmospheric pollution that could only come from industrial civilizations, or megastructures built around stars to harvest energy. The search for Dyson spheres and similar megastructures has become particularly sophisticated. Astronomers look for stars that show unusual infrared emissions, which might indicate artificial structures surrounding them. While several candidate objects have been identified, natural explanations have been found for all of them so far. One of the most famous examples is Tabby's star, officially known as KIC 846-2852, which shows irregular dimming patterns that initially defied explanation. Some researchers speculated that the dimming might be caused by artificial megastructures, but subsequent observations suggest that dust clouds are the most likely cause. The discovery of thousands of exoplanets has opened new avenues for SETI research. The James Webb Space Telescope and other advanced instruments can analyze the atmospheric compositions of nearby exoplanets, looking for biosignatures like oxygen and methane, or even more exotic technosignatures like industrial pollutants. Atmospheric SETI represents a particularly promising approach because it doesn't require alien civilizations to deliberately send us messages. Industrial civilizations might inevitably produce atmospheric signatures that we can detect from light years away. Even if aliens aren't trying to communicate, they might not be able to hide the effects of their technology on their planet's atmosphere. Some researchers have suggested looking for more subtle technosignatures, such as the coordinated dimming of multiple stars that might indicate large-scale engineering projects, or unusual isotope ratios in stellar atmospheres that might result from nuclear waste disposal or stellar engineering. The search has also expanded to include gravitational wave astronomy. Advanced civilizations might use gravitational waves for communication, as these signals can travel across the universe without interference. LIGO and other gravitational wave detectors now search for artificial signals among the cosmic gravitational wave background. Interestingly, some of the most promising SETI approaches don't require advanced alien civilizations at all. Searches for simple biosignatures could detect planets with primitive life, answering at least part of the Fermi paradox by demonstrating that life itself is common, even if intelligence is rare. The SETI community has also grappled with the question of active messaging, sending deliberate signals to other star systems rather than just listening. The Arecibo message, transmitted in 1974, was humanity's first attempt at interstellar communication. More recent projects have sent more sophisticated messages, including mathematical concepts, scientific information, and even artistic expressions. However, active SETI remains controversial. Some scientists, including Stephen Hawking, have warned that advertising our existence might be dangerous if hostile alien civilizations are listening. The debate over active SETI reflects deeper questions about how alien civilizations might behave and whether contact would be beneficial or catastrophic for humanity. Despite decades of searching, SETI has found no convincing evidence of extraterrestrial intelligence. But this null result is itself scientifically valuable. It helps constrain models of how common technological civilizations might be and informs our understanding of the Fermi paradox. Recent developments and new perspectives. The search for extraterrestrial life and intelligence has been revolutionized by recent technological advances and discoveries. The launch of the James Webb Space Telescope has given us unprecedented ability to study the atmospheres of distant exoplanets. Already, JWST has detected water vapor, clouds, and complex atmospheric chemistry on worlds dozens of light years away. Perhaps more significantly, we've begun to understand that the conditions for life might be far more widespread than previously thought. The discovery of subsurface oceans on moons like Europa, Enceladus, and even Pluto suggests that habitable environments might exist throughout the solar system, hidden beneath icy crusts and warmed by tidal heating rather than stellar radiation. These discoveries have profound implications for astrobiology. If life can exist in the dark oceans of Jupiter's moons, then similar environments might be common throughout the galaxy. Rogue planets, worlds ejected from their star systems and wandering alone through interstellar space, might harbor life in subsurface oceans for billions of years. The study of extremophiles on Earth continues to expand our understanding of life's possibilities. We've found organisms that thrive in conditions once thought impossible, in near-boiling water, in highly acidic environments, in areas of intense radiation, and even in the vacuum of space itself. These discoveries suggest that life might be far more adaptable and widespread than the traditional Goldilocks zone concept implies. Advances in artificial intelligence have also influenced how we think about alien intelligence. As we develop more sophisticated AI systems, we're beginning to understand that intelligence might take forms very different from biological cognition. Alien intelligence might be silicon-based, quantum mechanical, or based on principles we haven't yet discovered. The recent confirmation of interstellar objects passing through our solar system, such as Oumuamua and Comet Borisov, has raised intriguing questions about whether we might detect alien artifacts in our cosmic neighborhood. While these objects appear to be natural, they've demonstrated that we can detect and study visitors from other star systems. The growing field of astrogeology has revealed the incredible diversity of planetary formation and evolution. We've discovered planets made of diamond, worlds where it rains glass sideways, and systems so chaotic that planets are routinely ejected into interstellar space. This diversity suggests that the range of possible environments for life might be far greater than we ever imagined. At the same time, our understanding of humanity's own future has evolved. Climate change, artificial intelligence, biotechnology, and nuclear weapons present existential challenges that previous generations never faced. Our success in navigating these challenges might determine not only our own survival, but our ability to eventually become the spacefaring civilization that could make contact with others. The Fermi paradox remains unsolved, but our approach to it has matured. Rather than expecting a single answer, scientists now recognize that the explanation might involve multiple factors. Perhaps life is common, but intelligence is rare. Perhaps intelligent civilizations are common, but tend to destroy themselves. Perhaps they transcend physical reality, or hide from potential threats, or simply haven't had enough time to spread throughout the galaxy. What seems clear is that we are living through a pivotal moment in the history of our species and possibly in the history of life in our region of the galaxy. Within the next few decades, we will likely discover life elsewhere in our solar system, detect biosignatures in the atmospheres of nearby exoplanets, or receive our first confirmed signal from an extraterrestrial civilization. Alternatively, we might determine that life, while possible, is extraordinarily rare, and that consciousness is an even rarer cosmic accident. Either answer would be profound, reshaping our understanding of our place in the universe and our responsibilities as perhaps the only known conscious observers in our cosmic neighborhood. The alien paradox forces us to confront fundamental questions about existence, intelligence, and our cosmic future. Whether we discover that we are alone or that we are part of a vast community of conscious beings, the answer will mark a turning point in human history. Until that moment arrives, we continue to search the cosmos, driven by what may be the deepest question in all of science. Are we alone?